Okay. So the problem we have is we have a sphere, and a student wants to determine the value of acceleration due to gravity for a specific location, and sets up this experiment, which is a sphere falling down to this table, which is at a distance h up in the air, and this sphere is released when an electromagnet is turned off, which is holding the sphere up, and when the electromagnet is turned off, a timer is also turned on, and the timer stops when the sphere lands on the pad. So immediately looking at this question, I'm going to draw a free body diagram of the sphere at the moment it's released. So this is the sphere, and it has one force, which is just mg. And a few other things to note is that it has a v naught of 0, delta x is h, and those are some given. And some questions that could potentially be asked regarding this situation are, what is the distance h? And also, how long does it take for the sphere to fall? So those are some potential questions that could be asked. But just looking at the first question, it asks, while taking the first data point, the student notices that the electromagnet actually releases the sphere after the timer begins. Would the value of g calculated from this one measurement be greater than, less than, or equal to the actual value of g at the student's location? So this question is asking, once the electromagnetic pad is turned off, the timer has already started a couple seconds. So that means, let's just say, for example, it's delayed by 1 second. So it takes, the timer starts by 1 second, and then after that second, the sphere starts to fall down. So that delay would most likely cause the acceleration to be less than the actual value of g. And this is because if we look at the units for acceleration, it is a equals meters per second squared, and delta, the meters, which is h, that is a constant and it stays the same. However, if this time is changed and it is increased because of the delay of the electromagnet, and that means this m is being divided by a larger s, meaning that the overall acceleration would be a smaller calculated value than g. Yeah, and the second question asks, it regards this table, and it says, the electromagnet is now replaced so that the timer begins when the sphere is released. The student varies the distance h. The student measures and records the time, delta t, of the fall for each particular height, resulting in the following data table. Indicate below which quantity should be graphed to yield a straight line whose slope could be used to calculate a numerical value for g. Might not be clear in the camera, but here are all the values listed. for the varying delta h's and the delta t's. So so if we were to plot this out, if we were to plot out the data points given in this table, well, assuming that h is the y-axis and t is the x-axis, we would probably come up with some sort of linear line. However, knowing that slope equals y over x, that means, in this case, unit-wise, the slope of this line is the height over time. And we can see that this time is not squared, meaning that these units, if this is essentially equal to meters per second, this line would equal velocity. So the question is asking, how could we change this graph so that the slope of this line could be acceleration instead of velocity? And we could do that by basically just squaring this delta t, because if acceleration is meter over second squared and velocity is meter over seconds, then all we have to do is square these seconds to get the acceleration. So some new values would be 0.011, 0.045, 0.117, 0.16, and 0.2. So these values are obviously smaller than their original values. So we can graph this. We can graph these new coordinates. So this is time squared, and this is h. And our largest value is 0.2, so we would most likely split this up. And our largest x value is 1, so we would most likely split this up like this. And then here, if the largest value is 0.2, so if we're going to graph this out, it would be something like this. This would be the first point. This would be up here. .16 for 0.8, and then 0.2 for 1. So be something like this. And yeah, again, this makes sense because this slope is graphing h over t squared, and just the bare units, h is equal to m, and t squared is essentially second squared. And if we recall what we did over here, if the slope of a line is m equals y over x, then the slope of this line is m over second squared, which is acceleration. So yeah, this line, the slope of this line would show the acceleration for each given height according to its delta time squared. So yeah, pretty sure that's the end of the problem.